Good morning, students, and welcome to our CBNG 3009 video lecture series for the coursework on traffic engineering. By now, you would have done the practical work for the exercise at the intersection of the priority bus route and the Macoya Road. So today we're going to go through how we actually process that data and generate the intersection analysis. So for this course, we are going to be using the Highway Capacity Manual, that is the HCM 2010 methodology for computing what is called the level of service. The level of service essentially gives us a measure of how well the intersection is performing over particular periods. For example, the morning period, the lunchtime period, the afternoon peak, etc. So, level of service. What is level of service? Well, it is a scale according to the Highway Capacity Manual from A to F, A being the best, F being the worst, and having intermediate values. So, we have level of service A, which represents a delay of 0 to 10 seconds. Level of service B, 10 to 20 seconds. C, 20 to 35. D, 35 to 55 seconds. E, 55 to 80 seconds. And F, anything greater than 80 seconds. What does this mean? Well, I'll go through the definition of delay shortly, but essentially, it's delay associated with the traffic signal. So, for example, once you're delayed less than 10 seconds as a result of the traffic signal, you will be experiencing level of service A. In practical terms, level of service A would be as if you had no congestion at all and you were able to proceed through the intersection fairly easily. Level of service F, being the other extreme, would be what we call jam density conditions, or where we have chronic congestion essentially and you're in gridlock, so you cannot move. So, what do we mean by delay? According to the Highway Capacity Manual, delay, or what we refer to as control delay, is the sum of three terms. D1, some texts have it as common D, some have it as capital D, so we'll be using capital D for our coursework. D1 plus D2 plus D3. D1 here represents the control associated with strictly the traffic signal. So for example, as you approach the signal, if you were to meet the red interval or the red phase, a driver would normally proceed to press the brake lever, or the brake pedal, sorry, and then gradually come to a stop at the intersection. So the control delay that's associated with D1 is actually the delay from the time the driver depresses the brake pedal till he gets to a stop, and then until he reaches the green interval and is allowed to proceed. Right? So D2 is what we refer to as incremental delay. The incremental delay occurs when you actually have effects, upstream effects. For example, you may be in a fairly tight grid within a city or along an expressway where you have a series of signals, and because of the effects of signals upstream, the traffic stream is interrupted and the arrivals appear fairly disjointed or not in a platoon, so that this causes an additional delay outside of the control delay at that particular intersection. So that is what the D2 term represents in addition to D1. D3 represents what we call the initial queue delay. The initial queue delay, as the term suggests, is delay associated with queue at the start of your traffic data collection. So for example, some of you, particularly those in the afternoon session, would have noticed at the commencement of the traffic survey at 3 p.m., there may have been a queue at the particular intersection at one of the approaches. For example, the southbound approach would have had a queue. If we were to ignore the effects of that queue, then we would be underestimating the delay passengers or drivers, as the case may be experiencing in the traffic stream. So as part of the methodology, there is a way to determine or a formula or methodology to actually determine this factor, which then contributes to the overall delay D. Now, for the purposes of our coursework, because of how data intensive these two and the rigor required to collect these bits of information, we will be sticking strictly to the first term, D1, which is the control delay. That is, the delay associated specifically with the traffic control device, which is, in this case, a traffic signal. Now, just a word of caution, if you were to go through the high capacity manual, the figures that I mentioned before for level of service, that is the time 0 to 10 seconds, etc., all the way down to F greater than 80 seconds, are specific to traffic signals, signalized intersections on arterial roadways. If you were to look at the thresholds for levels of service on unsignalized intersections, for example, you would see that those threshold values are actually slightly different. So you have level of service values, for example, on freeways, you have for unsignalized intersections, two-way stop control intersections, four-way stop control intersections, and you even have level of service thresholds for pedestrians and cyclists. So just to be sure that we're on the same page, the calculations that we are doing for the purposes of the coursework are specific to signalized intersections. Okay, so just to reiterate, we will be focusing on D1. So our computation would be delay D, which we will use to compute our level of service. Will be strictly based on the first term. So, our formula for D1 is as follows. So this is what the formula looks like. So after explaining, I'll go through the definitions of all of these terms, so you actually have those in your notes. But essentially, C here, big C, is what we refer to as the cycle length. What is the cycle length? That is the time from the red interval to a subsequent red interval. And I'll explain that in a little bit more detail subsequently. G upon C. G upon C is the ratio of green for the particular phase. Okay? So you have the cycle length, for example, and you would have had green time for a particular direction. So the delay in a particular direction would be the amount of green time for that particular direction divided by the overall cycle length for the intersection. Cycle length, again, being the time from the red phase to a subsequent red phase. This is then divided by 1 minus the minimum of what we call the V upon C ratio, or volume to capacity ratio, which is given as V upon C. Again, the volumes that you would have computed in a particular direction divided by the capacity, which you will work out subsequently. So the dividend of that gives you the delay, the control delay. Right, so now that we have the formula, and again we'll go through these terms in detail, all the definitions, so it may seem a little bit confusing to you right now, but as we go through, then we'll explain all these terms and we'll see how we actually get to the capacity and so on. So big C, what is big C? Big C is cycle length. So we have our traffic signal. It's a red display, an amber display, and a green display. Each one of these displays lasts for a particular time, which is then referred to as the interval. So you will have a red interval, an amber interval, and a green interval. The way the traffic signal is set up at the intersection, as with most signalized intersections in Trinidad, is that initially you have a red, then you go to green. The green lasts for a particular time, then it goes to amber, then back to red. So the time it takes to go through that pattern, or what we refer to as a cycle, is called the cycle length. So the cycle length, just to be clear, would be the time from the initial red showing plus the green plus the amber and back to the initial red showing. So the time it takes to go from red to red. So beginning of red to green to amber to beginning of red is your cycle length. So the red interval will have a particular time. The green interval also has a particular time. The green interval is important because we use this to work out what we call the green ratio. Big G being the time for green divided by the cycle length. Recall in the formula to compute D1, which is the control delay, there was an element referred to as G upon C in the numerator. That's called the green ratio and is actually used for each particular direction. So in the case of our signalized intersection at Macoya and the priority bus route, we have two phases. One phase that allows north-south movements to proceed, and another phase that allows east to west movements to proceed. So we will have two green values, one for the north-south direction and another for the east-west direction. So we will expect to have two green ratios. Again, one for the north-south and one for the east-west. V upon C is also referred to as X. X, so both terms being similar, is what's called the volume to capacity ratio. The numerator we actually collect, the denominator we actually compute. And just to be clear, the difference between cycle length and the capacity is that cycle length is big C, capacity small c. So, volume to capacity ratio, as the term suggests, is the ratio of the volume that comes through the intersection compared to the theoretical capacity. Alright, so as you can imagine, it's a term that has a range between 0 and 1, theoretically. Now, why is that important? Well, as you go through our computations, and if you look at the level of service classifications in the high capacity manual, A, B, C, D, E, F. These all assume a volume capacity ratio of less than 1. So A being 0 to 10, B being 10 to 20, C 20 to 35, D 35 to 55, E 55 to 80, F greater than 80. So all of these values assume that the volume to capacity ratio is less than 1. If the volume to capacity ratio goes higher than 1 or is equal to 1, then automatically, irrespective of the delay, these values all convert to F. Now you may be wondering, under what circumstances we can actually have a volume to capacity ratio being greater than 1. Well, if the demand is a lot higher and capacity for the facility stays the same, which usually happens, then you can have the volume to capacity ratio being equal to 1, which triggers the F. You can also have instances where capacity is reduced, for example, in an accident, or if you have illegal parking, then you can actually reduce the capacity while having the same volume. So therefore, these values can actually, although the delays may be fairly small, you can still end up in a situation where you are under service F. So in your computations, working out the volume to capacity ratio is a critical component. Because irrespective of the delay value, D1 that you compute, if you were to get a D1 that is less than, let's say 80, let's say it's in the 55 to 80 range, but your volume to capacity ratio is equal to or greater than 1, then automatically you're at F. And that must be carefully noted in your report. Okay, so I'm going to go through a few more definitions. I went through the definition of an interval of some of the key terms in the delay computation, but some other key traffic engineering principles must be understood before we actually get into the data reduction component. So, a phase. What is a phase? Well, represented by the symbol phi. A phase is a group of concurrent movements with the right of way. Again, a phase is a group of concurrent movements with the right of way. So in the case of our intersection at McCoy, we have north-south, east-west. At any given time, we have either the north-south movement going, or we have the east-west movement proceeding. And these are the only movements, concurrent movements, allowed by the traffic signal system. So therefore, we would say that this is a two-phase intersection because there are principally two phases. So phi, we have phase 1, and we have phase 2. And just like the cycle length and intervals, these have times. Now, the phase is not the time strictly for the green, for these. It includes the amber. Okay, so in a phase change occurs at the commencement of the amber. So for example, you may have the north-south proceeding. As soon as it turns to amber, then the north-south phase terminates. Okay, now why is that important? Again, you recall the amber interval. There's a concept referred to as lost time. So there's time in the signal cycle that is underutilized or is not used at all due to a number of reasons. Right? So vehicles not being allowed to move, the reaction time for motorists once they get the green, that time that is lost in there, that is important, especially when it comes to how we actually set up the phases. So in principle, though, phases have a specific time and it's usually represented by phi. In more complex intersections, you will see, for example, movements, concurrent movements, looking something like this. You may have two through movement and a right turn movement together, whilst all other movements are not moving together. In another phasing plan, you may actually see a north-south movement together with a southbound movement together with a through movement and a left movement with a signal phase, and so on. So phases can come in a number of combinations, but the important thing to remember is that a phase represents a group of concurrent movements that are given the right of way. The right of way represented usually by a green symbol. Now, while the phases may have a certain time, diagrammatically, they are also represented like this. So if you were to look in typical traffic engineering texts, this is how you would actually see a phase diagram, or this is one of the ways I should say. There are many other ways, but this is typically how it's represented. So phase 1 would be like this, with the arrow showing the directions of the movements with the right of way. Phi for the number of the phase and the time, whether it's 10 seconds, 25 seconds as the case may be. And as you can imagine intuitively, the other phase will be represented by this diagram. Okay, so the phase concept. So next, we move on to the term or the concept of the peak hour factor. The peak hour factor is a measure of the variability of flow within the peak traffic hour and is denoted by PHF, represented by the peak hour volume divided by 4 times the maximum 15-minute volume within the peak period. So, as you would recall, or by now you would have gone through the traffic engineering exercise and would have recognized that the traffic data is stored in 15-minute bins, or 15-minute intervals if you like. The peak hour is the sum of 4 consecutive 15-minute periods within the actual study period. So, for example, the data would be recorded from 6 to 6:15, 6:15 to 6:30, 6:30 to 6:45, 6:45 to 7, 7 to 7:15, etc. The peak hour is the maximum of any of the 4 consecutive 15-minute periods. So we may have, for example, these 4 15-minute blocks representing the peak hour, or we can have these 4 consecutive periods representing the peak hour. So in other words, the peak hour does not necessarily have to start on the hour. It can start at 1:15, go for one hour there with 4 consecutive 15-minute periods. Just as well, it could start at 6:30. It can start at 6:30, sorry, and proceed up and end at 7:30. So, whatever those 4 consecutive 15-minute periods are, in determining the peak hour factor, we look for the maximum or the highest 4 consecutive 15-minute periods, and that term goes to the numerator. Then, the 15-minute period within that hour that has the highest volume is used in the denominator. And the dividend of that is the peak hour factor. So, let me do a little example just to explain. So let's say we had, in this 15-minute period, 150 vehicles, and we had 225, then we had 175, 100, and 300. Intuitively, 1, 2, 3, 4, 5, yes. So, if we were to sum these periods, we recognize that we have 10, 5 and 2, 7, 2, 9, sorry, 7, 14, 15, 5, 1, 2, 3, 4, 5, 6, 6, 15. And then in this period here we have 1, 7, 2, 9, 10, 5, 15, 1, 2, 4, 6, 9. So we recognize that our peak period, or peak hour in this case, with the limited data we have, would be from 6:15 to 7:15. So, in computing the peak hour factor, we would take the V60, which is 950, divided by 4 times the maximum value within this peak hour, the maximum 15-minute value. In this case, the maximum 15-minute value is 300. So we'll go 4 times 300. So we'll get 950 over 1200. And this value would give us the peak hour factor. Now, why is the peak hour factor important? Well, it is used to determine the theoretical capacity of the approach. Recall, when we were doing the volume to capacity ratio X would be computed by V upon C. Volume we collect in the field. Capacity, however, how do we determine capacity? We cannot physically determine capacity there because we literally don't know or we can't tell what the intersection or the approach can actually accommodate. However, based on the peak hour factor, which gives you a value within the range theoretically 0 to 1, but more practically in the range of 0.85 to 1. Based on the peak hour factor, the volume that you collect are divided by the peak hour factor, and that, according to the HCM capacity manual, gives us the theoretical capacity of the approach. So then the volumes that you collect would have to be adjusted, and the highway capacity manual speaks about it as adjusted volumes. The adjusted volumes are done based on dividing the collected volumes by the peak hour factor to determine the theoretical capacity of the intersection. And that is what you actually use in your computations for V1. Okay? So very important. So what does the peak hour factor represent again? Is the variability of flow within the peak hour. So if you were to have values, if these values were to be, for example, more like, well, let's say theoretically 200, 200, 200, 200, then clearly we can see that based on this formula, our peak hour factor would be 1. So 1 then represents uniform flow within the peak hour. As we have these values tend to be a bit more variable, so we'll be closer to the lower end of the scale. Okay? So then that means there's a fair amount of variation within the traffic stream during the peak hour. And so right away from this, looking at the peak hour factor, it can tell us how the traffic flow was proceeding through that particular peak hour. Okay, and our final definition before we end this particular sequence, saturation flow rate. Saturation flow rate, normally denoted by S, theoretically, is the maximum number of vehicles that can proceed through an intersection in 1 hour, assuming 1 hour of continuous green time. So we have our intersection, our signalized intersection. But obviously, we cannot determine saturation flow rate in the field because there's no intersection known in this world that will have 1 hour of continuous green. So, in order to compute the saturation flow rate, a compromise must be made. And so, manually, as some of you all would have done in the field, the saturation flow rate would have been computed by allowing a certain number of vehicles to pass the stop sign from an observer, looking at the stop sign, and then timing either the 5th, 6th, 7th, 8th, or 9th vehicle to pass the intersection. And doing this for a number of cycles until such time we develop maybe 20 to 25 points that we can actually compute the saturation flow rate. Right? Now, why is the saturation flow rate important? Well, theoretically, S naught, based on geometrics and models, etc., it is estimated that on an arterial, on an arterial, 1900 vehicles can actually flow through an intersection uninterrupted. More specifically, saturation fluid is represented by vehicles per hour green time per lane. Okay? So, just as the definition mentioned, the maximum number of vehicles that can go through the intersection in a particular direction, assuming 1 hour of continuous green. So the formula is, or the units of this, of the saturation fluid, theoretical saturation fluid, vehicles per hour green per lane. Okay, so why is that important? Well, in terms of determining capacity, we need to, if I may use the term, calibrate this term to better understand what the available capacity is through the intersection, along with the other terms that we mentioned before. So in your case, you would have actually gotten the practice of measuring the field saturation fluid both manually, and in some cases, some groups actually did them using the traffic counters. So that's one way, but there's also the theoretical saturation fluid, which is computed from, again, the highway capacity manual gives a specific formula for estimating that, and it's as follows. Okay, so you can see that the saturation fluid, the theoretical saturation fluid, contains a number of elements, some of which we must compute in the field, some of which is obtained by anecdotal data, and some of which you may have some from some other previous data sources. Right, so recall the theoretical saturation fluid, in our case being 1900 vehicles per hour green per lane. N here represents the number of lanes, and of course, for the particular approach, that is. In our case, there was 1 lane per approach, so N will be 1. But if you are doing a highway, for example, the Churchill Resort Highway right outside of the school, then N would be 3 for the highway lanes, and probably either 1 or 2, depending on the northbound or the southbound approach. Alright, so N represents the number of lanes. FW represents the lane width. Now, all of these items in the highway capacity manual, which is on the My E-Learning, contain formulae to compute these values based on data you would have already collected in the field. Okay, so no need to worry as you go through this session and the tutorial. A lot more of these terms will be explained, and if there's any information or any clarification you require, then we can so get. Okay, so the lane width, based on specific ranges, you have values. So in other words, what the highway capacity manual is suggesting is that the ability to move through an intersection is also dependent on the width of the lanes. So the narrower the lanes, you can imagine the less ability to actually proceed through the intersection. The wider the lanes, the more the ability, or the quicker you can actually go through the intersections. Or in this particular case, the more vehicles that can actually proceed through the intersections. The heavy vehicle factor. This should come as no surprise. The more heavy vehicles in a traffic stream, theoretically, the less the saturation fluid through the intersection. So you recall that in the classification, you're required to count heavy vehicles. Well, this is the reason why. Heavy vehicles have been statistically shown to have an impact on speeds through an intersection, on capacity and flows, etc. So as part of the theoretical saturation fluid formula, there's a factor to govern down, so to speak, the S0 value. Grade. So FG represents the grade. So essentially the slope on the approach, either negative or positive, has a particular impact on the ability of vehicles to go through. So you can imagine a fairly steep slope going through an intersection. Theoretically, assuming driver behavior is discounted, should allow more throughput of vehicles. Parking. So vehicles maneuvering to park on the side of the road have an impact on the flow of traffic. Again, intuitively, nothing strange here. And the impact of this is similar to the impact of a traffic signal on red. So for example, the maneuver required for parking would be to slow down first of all, and then proceed safely onto the shoulder, onto the parking spot. This obviously would have a ripple effect on vehicles in the queue, requiring vehicles to slow down and allow this vehicle to actually safely maneuver off of the roadway. So parking, so number of parking maneuvers does play a part in the ability of vehicles to flow through the intersection. Then we have the effect of bus blocking. So this you would have measured in the field. And so the number of, or the frequency of buses actually making stops, or in this case maxi taxis making stops, again has an impact on the flow of traffic. Now, if you look at the parking and bus blocking formulae, you recognize they have the same form, but rather different numbers. So the bus blocking and parking, they're essentially similar, but because of the types of maneuvers, they have slightly different coefficients. Okay? FA is area type. So whether you're in a built-up area, a rural area, a central business district, like in the heart of a city, there's a factor that, that is used to adjust the saturation fluid as well. And of course, slight variations, yes, but the area does tend to play a part in the way drivers behave. FLU, it's called the lane utilization factor. So in studies where we analyze multiple lanes, what we find is that drivers will not necessarily use the lanes 50-50. So on a two-lane roadway, for example, intuitively one may assume that 50% of vehicles may use the left lane, 50% of vehicles may use the right lane. It's not necessarily so. Sometimes there's a skewing in one direction. And actually, if you look at the regulations that require you to drive on the left except on overtaking, more than likely you would expect a bias on the left lane. So the lane utilization factor is essentially that. How much of which lane is being used actually within the peak hour? In our case, we have a single lane, so our lane utilization, of course, would be 1. But bear in mind that if we're doing a multi-lane facility analysis, then this lane utilization factor could be less or much less than the one that you would expect from a single lane facility. Right. Now, we have a special case with these last four terms. The Highway Capacity Manual was developed by AASHTO, that's the American Association of State Highway Transportation Officials. And of course, in North America, they drive on the right-hand side of the roadway. So, the left turn, this is for the left turning factor, this is for left turning vehicles, would be opposite to what we have or what we experience in the British territories or in the Caribbean. So for example, if you were driving in North America and you were at an intersection, at a signalized intersection, because you were driving on the right-hand side, you would have to wait on a traffic signal to make a left turn move, normally, and the most simplistic of intersections. However, in Trinidad and Tobago, we drive on the left-hand side. So in order to make a left turn, most times we do not have to wait on the traffic signal. We can filter into the left turn. Likewise, with the right turn, for them, they would typically filter into the right, whereas we would have to wait on a traffic signal to make a right turn. So what does that mean? Well, for the purposes of our analysis in the Caribbean, while using the AASHTO manual, these terms must be interchanged. So FLT becomes FRT, and FRT becomes FLT. So these are for right turning vehicles. So remember the turning movement counts that we had. When you apply the formula, ensure that the right turns that you actually recorded are actually switched for the left turn value and vice versa. Same thing applies for the last two terms. These last two terms represent the pedestrians and the bicycles. Okay, so we have pedestrian movements and we have bicycle movements across the intersection. These again we'll discuss in detail in the tutorials. However, I just want to emphasize the point that these terms must be interchanged. Otherwise, we will end up with the less of a factor and sort of a miscalculation of the theoretical capacity. Okay.